So now this is the third talk today, and it's also around the same theme, the use of functional principal component analysis. Also here in this context, most of this will be really vectorial, so it will be multivariate function. And this is joint work with Robin Sickles and One House Song. This is also the only paper that's not yet published, that's just under revision in econometric theory. Okay, so the talk is about panel data, analysis of panel data. And I want to start a little bit with the particular application motivating this approach, and that's an application to frontier analysis. It's not really very important in this because it's a panel data technique, and you may use it everywhere in panel data, but it's a little bit important in so far that we have a little bit of different focus than usual in panel analysis. So what we assume is the following: we have something like individual data observed over several time periods. And usually for this talk I assume that the number of time periods is relatively large. Large may be, well, I shouldn't start on the 12 or something like that. Yeah? So in our simulations that was our starting point, 12, 30, 120. Usually it will never be usually will not be as large as for these type of density things where you have thousands of observations. You will usually not have in this context. And so you have also something like n individuals, for example individual firms, and measurements at remember capital T of equidistant time periods. So the observations are YIT, XIT, YI is the response variable you're interested in. And you want to model as a function of the exponential variables x. So x is usually a vector of different variables. Okay, and for example in this application that motivated that, y will be the, say, production output of a firm, logarithm of, and x will be a vector of production inputs. And you want to estimate now production function and individual efficiencies of a firm. So the panel model in this context will be YIT, that's supposed to be a standard model, is something constant plus coefficients times the exponential variables, plus UI, that's an individual effect, plus standard error term, epsilon IT. Well, that's a standard panel model. You all know from, say, basic econometrics. And you know how to estimate that, these individual effects, depending whether you assume that correlations with the x's, you may use something like LSTV or GLS or whatever you like. Okay? In this context of this thing with the frontier models, the U's play an important role because they characterize efficiency of a firm, whether a firm is efficient or whether it is inefficient. The point is, you see, it just adds something. So if U is large, Y will be large. If U is small, for the same exponential variables, Y will be small. And of course a firm is more efficient if it produces more with the same inputs. So a firm will be more efficient if it has a large value of U, a large individual effect, and less efficient if it has a small U. Usually in this context these are normalized in such a way that the U's are just one-sided, is less or equal than 0, and the exponential function U, that's a score characterizing technical efficiency. Somebody who has is really efficient has the biggest possible U, which is just 0, and other one will have a large negative. But this normalization is not too important for practical analysis because it's just a question of normalization, just with the beta. If you change the beta, you may also have that the U's have mu 0. It's also possible. It's just a question of standardization. And it's not really important.
So x's are not necessarily continuous over time?
No, x is just some exponential variable. I don't want it to be continuous over time. I prefer x's which are very variable over time, and which are anything else but continuous. Usually I really assume also that, say, a time path of x are not smooth. That's even important. So the idea is it's like the y, time path of y's will not be smooth due to the epsilon. Right? And I also assume that the x's also have something like such an error component, which makes it non-smooth. It is important for what I want to do. The x's should be non-smooth. Smooth x's would pose problems. But let's come. So essentially, would be idea. It's just illustration of the standard panel model. These are, for example, all observations of, say, firm number 8. You have 8 firms here, and 8 time points per firm. So you see all these observations are very low. So this is inefficient. For firm number 1, here you see they are all very high. So this is an efficient one. So here the individual effect is large. Here the individual effect U is small. And that is quite important that these people in frontier analysis, this is a, well, say, a known community, which are own journals. And usually they do a lot of rankings of firms according to efficiency, also of hospitals and everything else. And sometimes it's very important for the firms to be ranked well, otherwise their stock markets will decrease. So there's a lot of money involved in these things. Okay, so the standard analysis, well, it's just a standard panel model. You have a usual assumption, the error term, expectation 0, where and sigma square, U individual effect, uncorrelated with epsilon. In frontier analysis, we will assume it's smaller than 0, but this is only a question of standardization. In standard panel data analysis, you will usually have that the U's also have mean 0 and some variance, the sigma square U. Okay, which is different from this sigma square. But as I said, you can transform this into that if you just change the beta. That's just a question of standardization. And analysis here based on standard method are just to fix the factor per least squares, LSDV. If you assume, for example, U and X are correlated. If they are uncorrelated, you generalize least or GLS and things like that. Okay? And the choice of an adequate procedure depends on the stochastic nature of UE and epsilon E. What we consider here now is a little bit of different things, that if you have a lot of time periods, for example, we had here data from US banking industry. We had observations about something like 10 years with 120 time periods, and there's a lot of things going on during that time, during that this decade. And in this sense, it seems to be a little strange that perhaps a firm should never change here in their efficiency. This individual effect should depend on time. That's the major idea. So there are well-known changes in business practices due to financial data regulations, and there may be possible time-varying technical inefficiency. It may just be that the firm bank was inefficient at the beginning, may be efficient at the end, or vice versa. So the idea is that the U's are, for example, depend on time.
What kind of data is that? How is technical efficiency defined?
Good question. This just a little bit is the efficiency was defined in this thing as a function of the number of loans given, right? Which, in a sense of the financial crisis, maybe. Well, okay. I mean, that was the standard way of measuring efficiency for these banks, right? And inputs, oh well, that's all types of variables. There's 12, 13 variables which define input things. Just characteristics, number of employees, how big is the bank, how much capital, and so on, right? But efficiency was function of the number of loans. So, okay.
That means the banks become more efficient, right, over time?
Well, they did. Oh, they did. Yes. Well,
efficiency differences between banks.
There are, first of all, efficiency difference between banks, but there may also be general changes in efficiency, right? So that, in a way, even, for example, this part may not vary very much, but for example, here the use maximum efficiency may change over time. In fact, it obviously did.
Or you still believe efficiency is a continuous, or it changes slowly?
Essentially, the idea is now that the individual effects are function of time, but not necessarily. We don't assume it's a continuous function of time. We also assume it's just something. What we have in mind is a smooth trend. And trend may be either function of time, linear function, but it may also be a random walk or something like that. This we also want to model. So we also want to deal with general stochastic process like random walks, which makes the whole thing very difficult. Okay, but you will see, okay? Okay, so... Okay.
So what are we looking at? Yearly data?
No, this is monthly data.
Monthly, so this is for 3 years roughly, right?
This is 10 years.
10 years?
10 years, 120 time period.
0 to 3, 30.
I think T is 120. Huh?
Monthly data, right?
What?
I see over 3 years, 36.
What is for 3 years? 84 to 95.
No, the plot, the diagram.
Plot goes only
Oh no, the plot is just an illustration. That has nothing to do with the data. The just illustrations. See, they may change over time. This is nothing.
nobody has told you to stick to the truth and to the facts.
I will show you that the results for the changing efficiency at the end. There's a data analysis.
Stick to the facts.
No, this was just to show you how it may change. That's not true. This has nothing to do with our estimates. Our estimates are much more degree. It's not linear function what comes up. Sorry, I should have said that. That's just a little bit to illustrate how it may change over time. Perhaps I should not have done it. Okay. Okay, so now our model we're dealing with. We have something, we assume that something like time varying individual effects. So that you have a standard panel model, have a panel model. This thing doesn't change. It's just beta times the coefficients. But now you have a function vi. The u is now a vi of t. Right? The individual function of time. And of course also the mean may change over time, so you have a general mean function, beta 0 of t, which may also depend on t. Okay? Oh, in this thing for identifiability, we'll just assume that the sum of the vi's is 0. Just not to identify this mean. Alright? And of course they have individual effects, and efficiency would then be just in every time period the maximum, the individual value minus the maximum value. Right? So it may change over time. Also the maximum efficiency may change over time. And the only qualitative assumption which we have, and which we try to say, that the vi of t represents smooth time trends. By smooth trend, I mean either it's a smooth function over time, or it's also, say if it's a random walk, usually people also say that's a smooth type of trend. The frontier is defined later. You see, this efficiency, if you have estimated the component of this model, you can calculate the efficiencies in this way. You take the maximum, the individual value of the vi minus the maximum value, and you get an individual efficiency depending on t.
I have learned that in frontier models, the epsilon are positive.
No. That's then you have learned something wrong. In standard panel frontier models, the u's are positive, are negative. The epsilons are just ordinary error terms. Mean 0. Usually these are positive, these have some, in this case it would be negative. But it's just a question of standardization. It depends on how you define beta.
So you don't have to call it frontier analysis, you can just call it partial linear modeling.
It's just the application, just to introduce. The point is, and just the application is only to motivate that we are mainly interested in this thing and not so much in this thing. Standard panel analysis would be to estimate most efficiently the betas. In the application we have in mind that betas are not very important. They are essentially nuisance parameters. We are interested in these things. Right? We are interested in the V's. So that's the only thing, the only reference to frontier analysis. That there the focus is on modeling individual effects and not on modeling the beta. Okay? And because the usual point of view in panel analysis is the inverse, where these are nuisance parameters. Okay? And the betas are the interesting things. In this application, it's just the other way around. That's the only thing where the frontier analysis comes into play. The only thing. Okay, now we come back to things with this function principal component analysis. In order to get this more efficiently and to be able, because, well, nevertheless, if you just consider that completely non-parametrically, you here have, for every r, you have one individual function. So you have a lot of individual functions over time. And you can improve precision of estimation, also interpretability, if you consider just something like this principal component models, where I say that it just exists on a dimension L, such that the vi of t can be described in this form as a linear combination of the basis function gr, which of course then are again principal components. And the thetas are the scores. And the only thing that differs, for example, the first is I assume that L is fixed, that there is an unknown dimension, I don't know L, but that there exists some L. This has long tradition in econometrics, this type of models, econometric factor models, which are quite often used, and where they often assume this type of L. There are also other people working with this type of model, like for Van Bay and then G and so on. And so this is the additional model assumption. This is something like a structure model. Okay? It's a model because it can be wrong. The L is fixed. Yes? Unknown, but it's a fixed L. But nevertheless, it's non-parametric because I don't say I know anything. I don't know L, I don't know G, I don't know theta. All this has to be estimated. And of course, the estimation process has to do with principal components, with smoothing and principal components. And the normalization is just such that G's are these eigen in this types, because I have just T now stands for T is 1 to capital T. It's just the panel, the periods. That's just a T vector. So essentially, I have a covariance matrix, not really an operator, because I don't assume necessarily everything happens in continuous time, or is interpretable in continuous time. But this normalization here is no restriction, and just then guarantees that the solutions, the G's that result, are just the eigenvectors of the empirical covariance matrix. Okay? So that's just the reason for this type of normalization. And all those, the L and all these things are unknown and have to be estimated from the data. Okay? And usually I really concentrate on this thing, also the beta 0, the mean doesn't interest me so much.
Why do you now use the series approach for your eyes?
The point is that this type of model is just what I said here before, that if you estimate these things, for example, the G's can be much better estimated, non-parametrically than the VI's. You always have information about the whole sample, all individuals. I mean, it's not very simple just to see if you have a bunch of curves, to see what's going on. This will help you much better to understand what is the structure of your sample. What's the underlying structure, because it's much simpler to interpret. So that's the major reason. First, precision of estimation. Second is better interpretation. Okay?
It works only if we really assume that beta J doesn't change through time as well.
Yes, that's true. That's a big assumption. I mean, here we are very general, and here we are just in the ordinary world. I agree. But it's really already quite difficult to deal with this thing. Okay? So, yeah?
And the way we define the thetas, has any relevance for the model? No.
The way?
Exponential form.
Oh no, this exponential form, that was only interesting frontier analysis. Forget about it for the rest of the panel data. Yeah. This was the theta. This is just the way to describe the VI's. And later on, if you want to calculate efficiencies, you use the exponential function. But that's a later approach. And if you're not in the frontier world, you may not want to do that. Yeah. It's of no importance.
So therefore, identifiability also summation of theta is 0. So average of theta is 0. It's a mean 0.
Yes, every theta I has mean 0. Right.
Okay, so this is more or less only the shaping very model idea.
Oh no. Shaping my model is something different. That's good.
Sure.
For reducing dimensionality.
It is a rejection of dimensionality, of course. I mean that the big qualitative assumption is the existence of a fixed L. That's smaller than T. The L is fixed but unknown. You don't know L. Right? You only say exists a fixed L. For many other classes you would have to fix it. It would be very difficult with an unknown number. But that's the big restriction. Yeah. That there exists some L, and of course that's a model. So that's a model aspect, so that which is no longer completely non-parametric. Okay? To give some examples of things we have in mind, for example, just for analyzing this type of data, for example, there's a very simple model of Connor, Schmidt and Sickles, which says just that the V is just a quadratic polynomial, okay? Which in this case would be, the model would be true with L equal to 3, okay? And the G's, well, normal would be after these things, okay? You don't have this orthogonality, would have to renormalize. But the G's would then span the space of all quadratic polynomials.
But probably it is not so bad that L is unknown, because it needs to define kind of oracle L and say that it's kind of L such all errors are small enough, and just compare as if we would know through L, and just to compare with matters with this.
Yeah, sure. At the end, you have to have a theorem which says that essentially you are able to identify L, yeah, if the L exists, yeah. So essentially, later on, in the theory, you have to say there is a way to identify L. Yeah. Otherwise, because you have to estimate it in a way. That's clear, yeah.
It seems that here you preset the function g. So
No, these are just examples. I just want to say these are special cases. I don't assume that this is true. Well, but this is a special case, maybe. So if this is the case, then it should find this one. Then it should find the quadratic polynomial. This is another model with other G's. This is only a problem model with L equal to 1, but a more complicated G. And this is another possibility. For example, also L equal 1, and the G may be a random walk. So this is something I want to keep you in mind, which is a major complication in this theory, because I have in mind that the V's may be functions like that means smooth functions over time, but it may also be something like that means a random walk. So, and the random walk, well, you have it for a period t plus 1, t plus 2, but it's not defined in between periods. Okay? So that's another possibility. So maybe a one component, but so the G is a common random walk that characterizes all the population, which is only realized with different intensity by this core parameter theta. So that's also a possible model. Okay, so these are some example models. What I also want to say, what's important to keep in mind in this type of model, with the thetas and the G's, identifiability of the model implies that all variables x, I, t, j possess a considerable variation over time. They should be not themselves be very smooth over time. Otherwise, I have difficulties to get this this thing and this thing to separate them. Right? I don't think it's too much of a big restriction, because also, for example, your response variable, the model says the path of y will not be smooth due to the epsilon. And it's also the idea that the x's have also such an error, such an independent component. So that's important. So for example, the explanatory variables, you cannot include time invariant variables. For example, I don't know, sex, if you have individuals. Yeah, sex is usually time invariant, doesn't change over time, and this doesn't fit into this thing. Well, sometimes there are people, okay.
But
And
the first part is actually mean function, and the second part is variance function. And why should be a problem if you have all the fixed effect on the mean and then random effect on the variance?
Well, the problem is a little bit how do you distinguish here between this is something over time, this is something over time. If this is very smooth, how do you distinguish between this and that? It's not very clear. It's not very clear.
So there are like you can read like this, like the first part is common to all observations, to all curves.
Yeah, but no, that's not quite true, because okay, the betas is common, but the x's they change by individuals.
Exactly.
So if, for example, the x's, okay, perhaps x is not so, but nevertheless, it's always also a sexual proportion. But for example, if for example x is just theta times a straight line, it's itself a theta times a straight line, individual theta times a straight line. which will have a hard time to distinguish between this and that. Yeah, the x's have an I. Yeah, and if, for example, the x's themselves are straight lines, which are just vary by some amplitude parameter, we will have a hard time to distinguish this and that. So usually you should not include time invariant demographic variables. You can show it's not identified. However, it's not so bad usually. But what you can do is, if for example, here's an example, a standard panel model with p time changing and q time invariant model. So, for example, you have p variables like this. These change with time, and you have another q variables where you have no t in it. And you see, this thing plus u, they just form one constant, right? One singular constant. And in our model, this would just be very simple. I have one component model, where the g is a constant function, and the coefficient is all that. So the theta in this model here is just these two things. And the g function is a constant. You see? Just rewrite it. You have here 1. Yeah? It's just a constant g function. And the theta IR is then this thing. So you cannot really distinguish between that. So in this type of p time series time invariant models, you would have to stick on this thing plus model this part by that. Nevertheless, it's not too bad. Usually, if for example it turns out later on your estimates the g is constant, no time changes, then you get estimate of the theta. Then of course you see what you can do. You have then the model theta I1 is equal to beta j xij plus ui, and you just can regress the time invariant parameters on the estimated scores, and it will give you an estimate of these thetas. Yeah? Because I mean it should just lead to this model that theta I1 is the sum over this beta j xij plus ui. The ui now acts as an error term, and this is just a regression model. So you can regress your thetas you get with respect to further time invariant explanatory variables in order to get these effects. But otherwise, all these effects will be there somewhere.
But is the x random then?
X is of course random, yes, everything is random. X is random, theta is random, g may be random too. If this is a random walk, that's random. Okay? I mean, I gave you an example here with a. Here, g's are fixed functions. In this case, that's a random walk. So the g itself is a random function.
Will that help if you standardize x's?
Well, I don't see what it would help. I mean, later on in our estimation procedure we standardize anyway. We standardize anything because we're interested in this thing, and first of all we want to get rid of the mean effect. But essentially it wouldn't help so much. So what is important, you have to keep in mind, this x, you only, for modeling in this way, you only have to use time changing variables x, and everything else, if you have sex or something which is not time changing, you have to find it out later on by regression on the thetas. Okay. So, estimation procedure. This is something we've already seen just in the other talks before. I just use, in this case, the empirical covariance matrix of the V's. Yeah? Just recall, you have this model that Vi of t is sum R1 to L is theta IR gr of t. And first of all, we estimate, if we knew these functions, we can decompose that and get the g's as principal components. Just our normalization is such that they are principal components. So you can form this empirical covariance matrix. Now it's really a matrix because we have now the vectors at the observation points 1 to t, at the time periods we observe. We have eigenvalues and corresponding orthonormal eigenvectors. And from this we can get the G's and the lambdas, just according to our normalization. Again, this is the basis property we have seen before. The problem is, of course, these are unknown. And so what do? We estimate it. So in the first step we estimate these things non-parametrically, just by partial least squares, the partial least squares approach. The only thing is a little bit that usually the kappa, so this is the thing. So what we do is a semi-parametric estimation of beta and vi, and then we determine beta hat, so the estimates of the betas for the x's, and functional approximations, mu I hat, by minimizing this type of thing. So this is just partial spline approach. We use the sum of squares. In order to get rid of the mean, we just center all variables, y bar, y and x, and minus, now this is our function approximation, and roughness is penalized by, well, so the usual type of spline roughness penalty, integral over the second derivative. And then we estimate the values vi at the time periods by just evaluating our estimate ui of t at t is 1 to capital T. The only important point here you keep in mind, usually in order, because later on we want to retrieve g from sigma, and here usually in order to get good estimates of the g, it's usually necessary to use undersmoothing kappas. Because, and okay, this gives you estimate of the betas, and of the vi hats. And then you can also represent this estimate in matrix notation, because the solution for this thing is just a natural smoothing, a natural spline, which you can expand on the basis. And this then gives, well, some matrix way to represent your estimators. That's the expression for beta hat. This is the expression for vi hat. And this is what is a smoothing matrix, which is just determined by a natural spline basis of order 2n. That's just, you can show the minimizer is a natural spline function. And so we can calculate that. So essentially, it's not so really difficult to determine the estimates. And from this, in the second step, you determine now from the estimated v hats, the empirical covariance matrix, calculate its eigenvalues and eigenvectors. And then we said this gives the estimate of the g functions, and from the estimate of g functions we can now by just simple least squares estimate the thetas, the parameters, the individual theta parameters, just by ordinary least squares, and this then gives the final approximation of yi in this form. Of course, later on in the last step you can also estimate the mean function by taking the mean of everything. Okay, just to show you some results of this procedure, some theoretical results. What we assume is an IID sample of individual units, and we consider asymptotic behavior as n and t tend to infinity, so simultaneously. We have no assumption which is larger, n may be larger, t may be larger, doesn't matter. And the smoothing parameter kappa used in the procedure is also may depend on n and t. The heavy assumption is that the dimension L is assumed to be fixed for all n and t. What is again assumed is that the time path of the explanatory variables have to be less smooth than the time path of the VIT, so they have to be some noise component which makes it difficult to approximate them by smoothing procedures. For example, it always works if, for example, the XRTs are pre-Q processes. And now everything also depends whether the V, the individual effects, the time-changing individual effects, and the X's, explanatory variables, are correlated or not. This is a standard question in econometric analysis. And they may be correlated, but rates of convergence improve if they are what we call ULC uncorrelated. And ULC uncorrelated means they are uncorrelated up to a linear component. There may be linear components of both who correlate, but linear components don't matter in this context. So So the non-linear parts of v and x must be uncorrelated. Then we call it ULC uncorrelated. Well, I'll show you some results, for example, in this context. For example, if we consider now that the case that the g functions of the v's are really smooth functions, like this quadratic polynomial, like these exponential functions we had in this context, where we have just the usual, something like usual non-parametric smoothing asymptotics, which would usually mean that in order to get to really use smoothness, you would have to do what is called a fill-in asymptotics. You have a time period, say, of 1 year, monthly observations, and if you sample more time points t, you get your time periods get narrower. So if you go over from 1 month periods to 1 week period, from 1 period to 1 day period, from 1 day period to 1 hour period, it would be a fill-in asymptotics. That means more t, more observations per curve, means denser observations. That would be the usual smoothing asymptotics. And in time series, in combination with non-parametric, sometimes these things are used quite often. Time series asymptotic is different. There you have fixed time periods, and if you say t to infinity, you add more and more equidistant time periods. So if you have monthly observations, t to infinity means more months. Yeah? Fill-in asymptotics means t to infinity means going from month to week and so on. That's a type of, and usually if you want to use smoothness, you would have to rely on this type of fill-in asymptotics. And that's, for example, the case which the smooth function, quadratic polynomials, exponential functions. And these are, for example, some type of the asymptotic results we obtain. We have cubic spline functions, for example, and we choose the smoothing parameter, something like nt to the minus 4/5. You see how this depends on the number n and the number of periods. Then we get something like that how the beta minus beta hat, how this is the rate of convergence. For example, the t, the rate of convergence for the g, depends on nt to the minus 2/5. And what you see here is, the only thing I want to emphasize is, usually if you estimate the individual vi, which is a smooth function in this context, you would have a rate of convergence of t to the minus 2/5. Because that depends, because then you only have the observations from one individual. For the g, you use observations of all n individuals, and so the rate of convergence is better. Depends on n number of individuals and the number of observations per individuals. And if you use that, then if n and t are, for example, approximately the same order of magnitude, you have that the difference between vi and this approximation you have here, with the estimated theta hat and g hat, is of a parametric rate of convergence, t to the minus 1/2. Of course, here only the individual information plays a role because the thetas, the parameters, are just only estimated from the individual data. Only the g's are determined from the whole population. But this, you see, is a parametric rate of convergence and not a non-parametric. Non-parametric would be n to the minus 2/5, not n to the minus 1/2. So you get a parametric rate of convergence. And it was also shown that the theta hats are estimated as efficiently as a parametric model with known functions, g. But we also consider another type of asymptotics. We have stochastic trends. We have no smooth functions. It's a smooth trend, but for example, a random walk. In this case, a completely different asymptotic plays a role. We have a time series asymptotics. T and anything corresponds to adding more and more equidistant periods. And nevertheless, here smoothing has an interpretation, even in this case. Usually you say smoothing is something, I assume a smooth function, twice continuously differentiable. There's nothing about twice continuously differentiability if you consider a random walk. But nevertheless, what you see, what you can show, that the bias of a spline approximation to random walk depends on the quality of the so-called cubic spline interpolant of this of this random walk, and there it can be shown that it depends on the second order differences. So if you just difference the process, and consider the second order differences, so you can show that the bias of your estimate is proportional to the second order differences of this approach. And this, of course, the big point is that if we have a random walk, for example, the value, the sum or the vi of t squares will increase. This thing is of the order t, whereas the second differences, they are stationary, is of order 1. And so in this case, what you get in this context is if you assume that, for example, the VIs are something like a combination of L independent random walks, then you also get rates of convergence. And for example, for the betas, this now depends whether x and v are correlated or not. You get better results if they are VLC uncorrelated. These are then quality of the estimates of the g. You see that has something to do with t minus 3/2 plus nt to the minus 1/2. And you also see the difference between vi and here the approximation by this model, by the estimated model, the relative error, is then of order t to the minus 3/2 plus nt to the minus 1/2, which in a way is already faster than that for the ordinary smooth thing. Okay, and this difference between theta hat and theta is of the order 1 over t. This just, you see, what we have done here, what makes the paper difficult, also difficult to read, is that we consider two different types of asymptotics in behavior. What user smoothness asymptotics fill in, and also time series things. We have, as an example, is random walks, just to get an idea. And general theoretic results now depend a little bit on many of these on this type of quantities. Yes, either, and we have some type of assumption that can be interpreted either under the smoothness asymptotics, where you say you sample more and more in a dense way, or for the usual time series asymptotics. There, of course, it depends a little bit. It usually it depends on, say, the sum, the average of the VIT squared. If this is a random walk, smooth process, then this will tend to infinity, as t to infinity. And the smoothness asymptotic, this will stay bounded. And theoretical results now depend on CT, BT, and DT, where CT is the rate of increase of this thing. BT is the rate of increase of the second order differences, and DT is the rate of increase of the x's. And our theory in a way works if this is more compared to that. So if the second order differences as a function of t are small compared to the original values of the original process. And for example, for a random walk, this thing will remain bounded with t. As t to infinity, this remains bounded, whereas this will increase with t. We go to infinity. For a random walk, the sum of squared elements goes up. Sum of squared elements. So that's the major thing. If this is small compared to that, we have something like a smooth process which we can approximate. And well, okay, these are, oh no, I got in the wrong direction. These are, well, a general formulation of the theorem. I don't think it makes a lot of sense if I discuss that here. You may want to consider it yourself. Just keep in mind these two examples I gave you with a smooth process and the random walks. What's only important here in this context, you got also results about the sum of the t minus l plus 1 smallest eigenvalues of sigma n, which under some certain standardization tends to a normal distribution. And this gives something, this relation may be used in order to estimate the dimension L. That's important here. Because theoretically, if the model holds with a fixed L, dimension L, then the sum, this sum here, all these true eigenvalues here should be 0. Because only from the empirical covariance matrix, only the first L eigenvalues are non-zero, all the others are 0. So the truth here will be 0. And this then says, well, this gives a bound to the estimation error that's from the empirical covariance matrix. How does it go? And this can be used just for approximation. Okay? So the choice of L is a little bit, we need an estimate of the error variance, which is done in this way. And then, well, we just use the result in before, which we just gave you here, that this term here should tend to standard normal distribution. Well, now we just replace this by an estimate, this by an estimate, and well, this is our test statistics. And if the hypothesis of L, for some L equal to 3, L equal to 4 is true, then essentially these statistics here should be smaller than say the 1 minus alpha quantile of a standard normal distribution. Because then this should be approximately standard normal. So this gives an idea. So the thing is, we choose L hat as the smallest L, so it's just this thing is smaller than the corresponding quantile of a standard normal distribution, just to use these theoretical results. And choosing parameter can also be chosen by cross validation, just the quality of the approximation by the G's. It can also be shown to work. Okay, so I just want to show you some simulations, just to end with. How they,
Well, why did you change from Kerner to now the Why did you change from Kerner estimation to the
smart splines? Oh, I've always been a fan of splines. But usually I'm quite flexible there. I use that what is simpler to analyze in specific context. I don't think there's qualitatively a big difference between kernel estimation and spline estimation. But for these implicit problems, where you also have to estimate other things, these are much easier. I mean, it's not quite clear how to determine this, because you estimate the betas at the same time. So it's not very clear how to determine the kernel estimate in this context. How do you define the kernel estimate? We want to estimate the beta at the same time as the v. It's not quite clear how to use kernel estimators in this context. I don't know. Kernel estimators are direct estimators. Huh? They say that's a squared sum of your y's, but this doesn't work.
So you could have
Because you have to get rid of the betas for the x's.
So if you have done just the least square estimate for only the beta part and the error residuals, you
Well-
do the same estimations as
I think this is how it
Yeah, well, maybe. But the point is, our theory, what we did there, what is important, what is important is the following, that we have, for this asymptotic theory, that I can show that the bias of a spline approximation has to do with the relation between the second order differences of the process and the values of the squared values, direct squared values of the process. That's a theorem you can derive for splines. I am unable to derive that for kernel estimators.
But that's because you use
And that is important, because you can say, usually the bias of non-parametric estimate, you say that depends on the second derivative of something. If you consider stochastic processes, like a random walk, there are no second derivatives. But there are second order differences. Right? And this is something to say this is small against this is something that is interpretable for smooth functions and for stochastic processes. That's the big difference. And that's something I can't show for kernel estimators. I think probably it's true too, but I don't know how to show it. I don't think usually in most cases there's a big difference, but it's also not so easy. I think splines are much more natural in this context, in my opinion.
Has this something to do with the penalty?
Yes, sure. It's just, you can show that the bias of a spline estimator is less or equal to kappa times the second, in the case of cubic spline, second derivative of the smoothing spline interpolant. In this case, even if it's not a function, it's a smoothing spline interpolant of your discretized values. You can interpolate that by splines. And for this interpolation, you can derive a second derivative, even if your function is only defined at some time points. And then you can also show the way this spline interpolant, the second derivative of the spline interpolant, if you interpolate a function v at time points t is 1, 2, 3, 4, 5, 6, 7, then the second derivative of the spline interpolant has to do with the second differences. This thing. So that's the essential point. Why this can be done. Okay, just to show you some simulations just to stop. We had here some simulation study with only 2 regressors. Yeah? So the p is equal to 2, not too much, with 30, 100, and 300 individuals and 12 and 30 time points. Yeah? T is 12 and 30. These 2 regressors. These are the betas, and regressors are generally called the VAR model, they're correlated. And now we assume a little bit how does our model behave in terms of different basic models. For example, if this is now in this simulation, that's the truth. We have a model with 3 components, L equal to 3, and it's just a quadratic polynomial. Okay? So, and for example, this is now the errors for the mean squared error of coefficients for estimating the betas. And this is the method I propose here. This is the method by Corwell, Schmidt, and Sickles, which is exactly the method which assumes that this is true. Whereas in our method, well, it's just what comes out. Well, and these are just the usual within and GLS estimators, without correlations. And what you see a little bit as error estimating coefficients, well, it's quite comparable here and here, whereas it's much worse in these cases with the usual standard panel models. Okay? And this is, for example, here also the case, then the error in estimating these things, that's the quadratic errors, mean squared errors. And you see, for example, also here you see the errors here in estimating the V's. Of course, this is better because it just uses knowledge, but it's not much better. It's only quite tiny difference. Where, of course, within and GLS, usual standard panel models who assume constant effects do not work. We cannot really approximate it. And these are the dimension estimates we get as an average over all the simulations. In a lot of simulations, in each replication we estimated L, and this gives just the average numbers of L's estimated. You see quite nicely the 4 components. This is the case when you have a random walk. So it was just the VI is a theta times a random walk. And this is, for example, the error in estimating the coefficients. And of course, here all these models are completely false. And so this is the best thing, especially if you consider here the error in estimating the G, the random walk G. Of course, I mean, this is, as you see, these errors are really comparably small, whereas these ones are much worse. Of course, they are wrong models in this case. This is for N is 30. These are different situations with different NNTs. And this is just the average, again, the estimated dimension from the model. You see, it seems to work quite well. The error is much larger than before. This is a standard panel model, well, perhaps not so interesting. And this is just another thing where we have 6 components, quite mad thing, something like a quadratic polynomial, a random walk. There's a 4th component, and then 2 sinus components. And for example, these are then the errors in estimating the betas. All these other models, which of course don't take into account the time changing effect, or not correctly, are very bad. And here you see now the error in estimating all these things, and you see, of course, seems to behave quite well. Also, at least in the case if you have more observations, also the dimension is fairly well estimated. So you see, in the scenario with quite small NNT, it's underestimated the L to 5 and not 6. Okay, and just finally, because Wolfgang wanted to see a little bit the changing effects.
Waiting is a question. Waiting is a question.
These are essentially the maximum of the VITs. It's a little bit this type of analysis which I did for these banks with these loans as efficiency measure. Also, some of the explanatory variables are more outputs than inputs. Yeah, which, okay, they have also theory about when this is allowed and when this is not allowed, okay. But nevertheless, I have a bit, I think it's difficult to interpret that, what it really says, what it really does. I mean, they do that all the time. It has also been very influential in this area. Just the efficiency of banks and so, this has also been an argument to say, well, you see, our banks have become more and more efficient, so you should do some deregulation too, right? This has always been the deregulation argument. So as far, I mean, I'm not too happy with all this, with this type of applications. Just from general, it's just the type of application that's done very often in this area. And I think from this what we get out, it's certainly one of the most serious in this respect. Because we have least assumptions. The only thing I always think is a problem in this context is that, well, you see, efficiency goes up. It's true, because the efficiency is the number of loans given. It went up by the deregulations. It's only what you can't foresee about, and there's nothing wrong about that. It's only what you couldn't foresee is that at the end it would just ended up in the bubble, right, which went down again. Which of course you will never see in such a type of analysis. There's no way to do that. Very comparable to this test of the dimensional. I think I gave you the paper. It's in there. I have no it's not on the slides, no transparencies now, and so it's a bit. And honestly, I had to look at it to remember exactly how it worked. But it's based on very similar results. Say the base. It also has to do with this test procedure for the dimensionality L.
So does that mean actually I actually had a difficult invention of that kind of hypothesis testing? But you have also some sort of a comparison. Is that be done in this way of testing instead of having automatic computation done in computation? Since the hypothesis is the same.
Well, the hypothesis would be, for example, as I said, a linear hypothesis. Yeah, so it means very specific G's, specific L is true. Of course, I mean, for example, in our thing, there's a straight line, because we end up with a test dimension. Our estimated L here was 7, right? And so a straight line can't be, because this is only L equal 2. So in L equal 2, the dimensionality L equal 2 is already excluded by, because we would have accepted dimensionality L equal 2 if the dimension test had accepted dimensionality L equal to 2. So it's always, we have already the dimension test says the straight line is not okay. Right? Already the dimension test says that. And then the second part of the test is then that you can test. Then you have a specification of the basis function, whether a quadratic polynomial or something like that, at the right dimension, and a certain specification, well, this specification fits it. So that's the other type of test you can do. Right? And this has all to do with the same thing with this type of results I showed you, which allows for the dimension test, which also gives you a links test. But we can construct confidence intervals in the usual way. That we can't anymore. But we can test.
All right. More questions? No. Then tomorrow at 10 o'clock, or is it also 9:30?
I think 9:30. Yeah. 9:30.